Q-learning is off-policy reinforcement learning algorithm that seeks to find the best action to take given the current state. It is considered off-policy because the Q-learning function learns from actions that are outside the current policy, like taking random actions, and therefore a policy isn't needed. More specifically, Q-learning seeks to learn a policy that maximizes the total reward. With that in mind, let's talk about the basic concept of Q-learning in reinforcement learning. I'm Thiruvan Jayavikrama and welcome to the topic of Artificial Intelligence, Chapter 2. Q-learning is a model-free reinforcement learning algorithm. Also, Q-learning is a value-based learning algorithm. Value-based algorithms update the value function based on an equation, particularly Bellman equation, whereas the other type, policy-based, estimates the value function with the greedy policy update from the last policy improvement. Can you remember? In our primary school, our school teachers rewarded us with stars once we had done school works properly. This is what happening in reinforcement learning. The Q in Q-learning stands for quality. Quality is, in this case, represents how useful a given action is in gaining some future reward. When Q-learning is performed, we create what's called a Q-table or matrix that follows the shape of state's action, and we initialize our values to 0. When the update and store our Q values after an episode. This Q table becomes a reference table for our agent to select the best action based on the Q value. The Q functions use the Bellman equation and takes two inputs, state as S and action as A. Using this function, we get the values for Q for the cells in the table. When we start, all the values in the Q table are zeros. There is an iterative process of updating the values. As we start to explore the environment, the Q function gives us better and better approximation by continuously updating the Q values in the table. Now let's understand how the updating takes place. Let's say that a robot has to cross a maze and reach the endpoint. There are mines and the robot can only move one tile at a time. If the robot steps onto a mine, the robot is dead. The robot has to reach the end point in the shortest time possible. The scoring reward system is as below. The robot loses 1 point at each step. This is done so that the robot takes the shortest path and reaches the goal as fast as possible. If the robot steps on a mine, the point loss is 100 and the game ends. If the robot gets power, it gains 1 point. If the robot reaches the end goal, the robot gets 100 points. Now, the obvious question is, how do we train a robot to reach the end goal with the shortest path without stepping on a mine? Each of the colored boxes is one step. Let's understand each of these steps in detail. Let's initialize the Q table. We will first build a Q table. There are n columns where n the number of actions. There are m rows where m is the number of states. We will initialize the values at 0. The combination of steps is done for an undefined amount of time. This means that the step runs until the time we stop the training, or the training loops stop as defined in the code. We will choose an action in the state based on the Q table. But as mentioned earlier, when the episode initially starts, every Q value is 0. So now the concept of exploration and exploitation trade-off comes into play. We'll use something called the epsilon greedy strategy. In the beginning, the epsilon rates will be higher. The robot will explore the environment and randomly choose actions. The logic behind this is that the robot does not know anything about the environment. As the robot explores the environment, the epsilon rates decreases and the robot starts to exploit the environment. During the process of exploration, the robot progressively becomes more confident in estimating the Q values. For the robot example, there are 4 actions to choose from: up, down, left and right. We are starting the training now. This robot knows nothing but the environment. So the robot chooses a random action, say right. In the case of the robot game, to reiterate, the scoring reward structure is power equals to +1, mind equals to -100, and end equals to +100. We have to repeat this again and again until the learning is stopped. In this way, the Q table will be updated. As for the summary, we discussed that Q learning is an off-policy reinforcement learning algorithm. We learned that Q learning uses future rewards to influence the current action given a state, and therefore helps the agent select best action and maximize total reward. So I hope you all learned the basic concept on Q learning, but hopefully this is enough to get you started and interested in learning more. So that's a wrap up for chapter 12. I'll see you around.